right, welcome. Here we are to a discussion of section 11.1 on sequences. We have, holy moly, a bunch of exercises. But as you'll see, a lot of these exercises may relate to new stuff, but a lot of them may relate to old stuff as well. A lot of this chapter, a lot of this section, rather, excuse me, not this chapter, but a lot of this section is about refreshing us of limit facts from either 141 or 132. So, let's just hold on tight and go down memory lane, working in the knowledge of sequences that we have every step of the way. So what is a sequence? Right, it's an ordered list of numbers, nothing more than that. And right, what are we talking about when we say this? We're saying that, well, as n goes to infinity, or as n approaches infinity, the value of the ANs approach 8. It's nothing more than that. We're not saying that the value of the ANs are 8, but we're saying that the values of the AN get close to 8 as n gets large. So maybe the values of an are never even 8, but they just get as close to 8 as you could ever hope. And that's what we mean by convergence of a sequence. What do we mean here? Oh, here we're saying as n gets large, the a sub n's become large and large and large without bound. And well, that's exactly what we've got here. So the an's become large as the n's become large. And really, it should say boundlessly large here, just to be precise. But whatever, they weren't precise, that's fine. All right, list the first 5 terms. Hey, this is just a function, people. It's a function where you can only plug in counting numbers. So you can't plug in pi, you can't plug in 1.2, but you can plug in 1, you can plug in 2, you can plug in 3, and so on. And if you do plug in those things, well, 1, 2, 3, 4, and 5, you'll get 5 things popping out. Make sure you keep track of the fact that -1 raised to a power is either 1 or -1, depending upon whether or not you have an even or an odd power on that -1. So that's something to look at, and well, nothing too much there. Similar story here, plug in 1, plug in 2, plug in 3. Just a function, people. Sequence is just a function where you can only plug in positive counting numbers. Now, here we have a recursive presentation of a sequence, which is slightly different from the previous in the sense that we don't have a functional expression exactly. What we have is like dominoes. We're told what the first one is, and we're told how to get the next one from the previous. So when I read n plus 1, I'm reading that as like the next sequence term. And when I read a sub n, I'm viewing that as like the previous, because a sub n would be the previous term to a sub n plus 1, right? Because a3 would have a2 as its prior, and a4 would have a3 as its prior, and so on and so forth. So if you think about this, then a sub n plus 1, the next is twice the previous plus 6. Well, if the first is 3, the next is twice the previous plus 6. So twice 6 plus 6, I get 12. Twice 12 plus 6, you get the next one. Twice whatever you got there plus 6, you get the next one. Twice whatever you got plus 6, you'll get the next one. And that's the nature of recursion. If you like computer science, there's a for loop in there. That's really all that's going on when you have a recursive definition of a sequence. Okay, why is this not going down? What is occurring here? Are we wigging out here with the video feed? Unclear. Oh, okay, and I think we're back. I thought we were back. I saw it do something, and unfortunately, okay, we're back. Sorry about that. Formula for the general term a sub n. Right, so now this is a sub 1, this is a sub 2, this is a sub 3, and what you want to notice is downstairs we have higher and higher powers of 3, whereas upstairs we're taking 5 and just multiplying it by 2. And so, or better said, we're taking -5 and multiplying it by -2 or something like this. So downstairs, initially we have 3 to the 0 or 1, then we have 3 to the 1, 3 to the 2, 3 to the 3, and so on. So each of those denominators would be 3 to the n minus 1, because the initial denominator for n equals 1 is 3 to the 0. And the second denominator is 3 to the 1, which is 3, and the third denominator is 3 to the 2. So we're sort of down 1 index on our exponent. Upstairs, we just have -5 times -2 to some power. In the first case, we have -2 to the 0. In the second case, -2 to the first. In the next case, -2 to the second, and so on. Right, since we're taking -5 times that factor of -2, life is good. Another way to see this, since we have minus 2 to the n minus 1 upstairs and 3 to the n minus 1 downstairs, you could just do minus 5 times 2 over 3 to the n minus 1. Just meld that together as one fraction, because indeed, to get from one term to the next, you just multiply by minus 2/3, maybe a similar way to see it. Next here, now is where we're getting into the Calc 1. This is a lovely trip down memory lane. Note, we've got an equal heavy rational function, and we want to take the limit as n goes to infinity. So yes, you could multiply by 1 over n squared top and bottom and see how that plays out. But if you did, what would you end up with? You end up with 2 over 2, which is just 1. You essentially pluck off the leading coefficients when you have equal heavy rational functions. Here we have a top heavy rational function, and so the top is going to grow much faster than the bottom, and who cares whether this goes to infinity or negative infinity, it diverges nonetheless. A beautiful nature of the word diverges is that it encompasses both positive infinity and negative infinity at once, so we don't really precisely care whether or not our limit is infinity or minus infinity, just that it's not a real number. So that's a savings, people. Like we should be fond of that term. Right, next, we essentially have n to the power 1/2 on top and bottom. If you multiply top and bottom by 1 over square root n, you would be able to see that we end up with 8 over 1 whenever n goes to infinity. Because multiplying by 1 over square root n, we'd have 9 over square root n downstairs. And that 9 over square root n would go to 0 as n gets large, and that's where you end up with the 8 over 1. So essentially, this is an equal heavy situation, even though it's technically not a rational function because the powers are fractional. Here, also, the powers are not fractional in part A, but you are bottom heavy. As n gets big, that thing's going to 0. Here, as n gets big, the power's going to 0. But if the power's going to 0, you're ending up with e to the 0, and e to the 0 is not 0. E to the 0 is a number to the 0th power, which, as always, is 1. So that is that. What about 10? Oh, okay, so here, yes, the minus 1 to the n sort of bounces positive to negative and positive to negative, but what's happening to the denominator as n gets big, that denominator is getting big, and so you essentially have 1 or minus 1 over an enormous thing, which is practically nothing, and so you end up with a limit of 0. This is essentially a bottom-heavy rational function because that minus 1 to the n contributes nothing other than a 1 or a minus 1, and the n that's growing downstairs is just destroying that 1 or minus 1 in terms of the influence on the expression of this sequence value. Here, I want to put that e in the denominator, and then I want to use L'Hopital. Because when I put the e in the denominator, I end up with infinity over infinity. If I don't put the e in the denominator, I end up with infinity times 0, which is still indeterminate, so I'm going to have to take the 0 and throw it in the denominator anyways. Or I can throw the n squared downstairs, in which case I get negative exponents upstairs and downstairs. But in either case, you're going to have to use L'Hopital. And so I would use L'Hopital to do this. That's a nice flashback down memory lane as well. This one is deceptive, right? Because if you just write it out, you get infinity minus infinity. And naively, you think infinity minus infinity is 0. But be careful, infinity minus infinity is not so fast. What we really should be doing is using our ln properties and getting ln of n plus 3 divided by n. And now, when you take n plus 3 over n, that equal heavy is going to go to 1, and you essentially go to ln 1, which is still 0, but the value here is 0, not because of infinity minus infinity, but rather because of ln of 1. Key distinction. Here's a situation where you could get the right answer, and if it was on a test, you could lose a lot of points, even though you may have gotten the right answer, because you sort of violated our indeterminate form knowledge, because infinity minus infinity is indeterminate. We can make infinity minus infinity positive infinity, negative infinity, or any real number in between. That is just a fact of the matter, and we could cook up examples for that, but that's more for class time. Right. Did we just wig out again? Oh, come on. Hopefully this is coming back to life here. I'm trying to be patient with this. What is occurring? That feels, okay, it feels like we're back. All right, we are back. Okay. A sub n equals 1 over 5 to the n. Hey, as n gets large, that denominator is getting gigantic. The numerator is just 1. Here, similar story. While the numerator is going up and down and up and down, the numerator is never getting bigger in absolute value than 1, which means the numerator is bounded, the denominator is unbounded, and hey, that's a classic recipe for 0 in the limit. Arctan, wow, double check this, right? As n goes to infinity, ln n goes to infinity, so now we need to know arctan infinity. This is a classic. It showed up on the final exam last semester. Arctan infinity is what, pi over 2, right? Because you're taking the tangent function, one little piece of it, and you're reflecting it about the line y equals x, and you've got this thing that goes up to pi over 2 off to the right and down to minus pi over 2 off to the left. If you don't know the arctangent function, put it into Desmos, take a look at it, and take a snapshot in your mind. I'm not saying it is going to show up, but if it does, my gosh, it's one of those things where it's really hard to do if you don't know that fact. Right, determine whether the sequence converges or diverges. Well, as far as this sequence goes, whether or not we converge or diverge, I see no convergence here, because no matter how far you go into the sequence, even though you get a bunch of zeros, you end up getting a 6. And every time you get a 6, you don't get convergence, because to get convergence, the sequence has to be such that after a certain point, you get as close to 0 as you want. And you can never get as close to 0 as you want, because even if you just wanted to get within a few units of 0, you'll never get within a few units of 0, because after every n, eventually there's a 6, and that's a problem. So this is a classic example of bounded divergence. We essentially have oscillation here, which is preventing convergence. Oh gosh, that denominator is just enormous in comparison to what's upstairs. If you play this out technically, you can see that you can factor out the minus 1 to the n, and then after the first 2 terms of the n factorial, you'll just have 2 over 3 and 2 over 4 and 2 over 5. And yeah, that thing is just going to 0 super quick like. Here, the numerator, this n over n plus 6 is going to 1, but now you have this minus 1 to the n. So this thing is essentially oscillating between 1 and minus 1 and 1 and minus 1. And that oscillation is going to be just like this guy up here, although even more profound, because every other term is positive and negative, 1 and minus 1, and or close to 1 and close to minus 1. And yeah, that's going to diverge as a result of bounded divergence. Right, is this necessary? Oh my goodness. So since this limit is true, you could use the limit laws here. And if you did use the limit laws, you'll get 2 minus 2. So is that true? Is that true? I'd have to really think about that, because couldn't we set up a situation where an plus 3, no, because both of them are getting as close to 2 as we want. And so their difference is going to be as close to 0 as we want. Yep, that's got to be true. So, right, this is true. If the differences were not as close to 0 as we want, we wouldn't have convergence to begin with. So the limit laws apply because the limit exists in this case. What do we got here? Oh, something between 1 and minus 1. Now here, you got to imagine this number times itself many, many, many times over. So take something like 0.98 or minus 0.98 and multiply it by itself many times over. You'll get a smaller and smaller, smaller thing until you end up getting something that's practically nothing. Wow, there are a lot. Holy moly, let me speed up. If a and bn are divergent, then an plus bn is divergent. Not so, right? Because the an's could bounce from 1 to minus 1, and the bn's could bounce from minus 1 to 1, and when you add them up, you just get 0 every time. That doesn't diverge, that converges to 0. Right, the products here, see, this is a similar story, right? Because you could have something that is boundlessly diverging here and boundlessly diverging there, like 1, 0, 1, 0, 1, 0, and here 0, 1, 0, 1, 0, 1, and when you multiply together, you just get 0, 0, 0, 0, 0. So that would be convergent. So yeah, 2 divergent things don't necessarily multiply to be divergent. There's no such property as that. Now 2 convergent things multiply to be convergent. 2 convergent things, sum is convergent, but the divergence, no, not so much. Right, decreasing, an is greater than 0, then an is convergent. No, right? Oh, an is greater than 0. That's important, right? So we have decreasing, but we are bounded below by some positive thing. Now that's where the monotone convergence theorem or the brick wall theorem comes into play. So that's an important fact, the monotone convergence theorem. If we were just decreasing and didn't have this restriction on what our an's were bounded by, then yeah, we couldn't say that we converge. But the fact that we are bounded by something below means that in fact the greatest lower bound rather would be our limit. And are we almost done? Yes, we are almost done. So, right, if this limit is L, then that limit's L. Sure. I mean, in both cases, look, all you're doing is letting the thing you're plugging into your function get big. And so no matter how fast you let that thing get big, if as n gets big, you get L, you're going to get L in both of those cases. You might get L a little bit quicker in the one on the right, but you're converging to L in both cases by the definition of convergence. That was a long one. Let me cut it off here because I've said enough.